Two waves, wrong angle, giant ships. Gone, the ocean doesn't need a storm to kill you. This is a cross sea. There is a photograph taken in 2010 off the coast of Algeria. A research vessel is listing badly to port. Its hull is intact. Its engines are functional. There is no storm visible in the image, no waterspout, no rogue wave towering above it. What the photograph captures, if you know what you are looking at, is a ship caught in the grip of two separate oceans arguing over the same piece of water. The waves are not enormous. They are simply arriving from two completely different directions at once, stacking against each other in a geometric lattice that no hull was designed to absorb. The ship does not look like it is sinking. It looks confused. And that confusion, as maritime engineers will tell you, is exactly what makes cross seas among the most underestimated dangers in the world's oceans. The sea has many faces, and humans have spent thousands of years learning to read them. Ancient Polynesian navigators could detect swells hundreds of kilometers from their origin by lying flat in canoes and feeling the rhythm through their bodies. Medieval European sailors watched the color of water, the behavior of birds, the angle at which the horizon met the sky. Modern meteorologists track pressure systems across hemispheres in real time. And yet cross seas, this precise, mathematically predictable interference pattern that can appear without warning in calm weather, under clear skies, in waters where the barometer has barely twitched, continue to catch mariners off guard. They kill ships. They kill people. And they do so with an almost architectural precision that, if you understand the physics, is both terrifying and beautiful. To understand what a cross sea is, you must first abandon the common mental image of ocean waves. Most people, when they think of waves, picture something like a moving wall of water, a single ridge building in one direction, cresting, breaking. This image, while useful for surfing lessons, is a dramatic simplification. In reality, the open ocean is almost never dominated by a single wave system. It is a superposition, a layering, of dozens of different swells traveling simultaneously from different storm systems, different distances, different angles, all moving through each other as if the water itself were a kind of conversation. A cross sea occurs when two of these wave systems are not merely present simultaneously, but are traveling at angles so divergent, typically greater than 60 degrees, that their interaction creates a visible, regular, grid-like pattern on the surface of the ocean. The result, photographed from above, looks like a vast checkerboard of water. It looks almost peaceful. It looks, to the unfamiliar eye, like something produced by a computer rendering for a physics demonstration. It is, in fact, one of the most dangerous sea states a vessel can encounter. This is not a historical curiosity. The waters off the coast of Isle de Ré, a French island on the Atlantic coast, are among the most frequently documented locations for cross seas on Earth. The stretch of ocean between Iceland and the Faroe Islands generates them regularly. Parts of the Pacific off the coast of California, the waters surrounding Taiwan, the mouth of the Persian Gulf, all known to those who study them as cross-sea territories. In 2019, a cruise ship encountered a cross-sea pattern in the North Atlantic severe enough to breach windows on an upper deck and send passengers and crew to hospital. The ship was 300 meters long. The waves that damaged it were, individually, unremarkable. The scale of the threat is not always visible in the size of the waves. It lives instead in their interaction, in the way energy from two directions combines to produce peak amplitudes that can, for a fraction of a second, dwarf the swells that created them. It lives in the unpredictability of where those peaks will appear, in the way a ship's hull is exposed to forces arriving not longitudinally, as it was designed to handle, but laterally, diagonally, and from directly below. It lives in the rhythm, or rather the absence of it. Single swell seas have a beat, cross seas have none, and a ship that cannot predict the next blow cannot brace for it. By the time this script reaches its end, you will understand not just what a cross sea is, but how it forms, what it does to ships at a physical and structural level, why certain regions of the world produce them reliably, how humans have tried, and repeatedly failed, to design around them, and what the growing instability of global weather systems means for the future frequency of a phenomenon that needs no storm to kill you. You will understand why the photograph of that Algerian research vessel tells a story that a photograph of a hurricane never quite manages, because the hurricane announces itself. The cross sea simply arrives. The physics of waves begin with EN. RGY, not water. This is the first thing that ocean science insists upon, and it is the first thing that most people find counterintuitive. When a wave moves across the surface of the ocean, the water itself does not travel with it. Individual water molecules rotate in circular orbits, technically called orbital paths, and return almost to where they began after each wave passes. What moves is not the water. What moves is the energy that was deposited into the ocean when wind first disturbed its surface, sometimes thousands of kilometers away and days earlier. A swell rolling past the Canary Islands on a Tuesday afternoon might carry the ghost of a storm that raged off Newfoundland the previous Friday. This distinction, energy traveling through a medium rather than the medium itself traveling, is the foundation on which all wave physics rests, and it is what makes the phenomenon of cross seas physically possible. Two swells can occupy the same patch of ocean simultaneously because they are not competing for the same water molecules. They are adding their energies together, and the mathematics of that addition, called wave superposition, is precise, predictable, and in the case of cross seas, architecturally spectacular. Superposition works like this. At any point on the ocean's surface, the height of the water at any given moment is the sum of the heights that each individual wave would produce if it were traveling alone. When a 2-meter swell from the northwest and a 2-meter swell from the southwest both reach the same point at the same moment, and both are at their peak, the water rises to 4 meters. When both are in their trough simultaneously, the water falls 4 meters below baseline. When one is at its peak and the other at its trough, they cancel almost perfectly, and the surface appears momentarily calm. This is constructive interference, when peaks align with peaks, and destructive interference, when peaks align with troughs, and the pattern they create depends entirely on the angle between the two systems and the difference in their wavelengths. For two wave trains traveling at roughly 60 degrees or more to each other, the resulting interference pattern on the ocean surface takes the form of a grid. Mathematicians call this a spatial interference pattern, and its appearance is not merely analogous to a checkerboard. It is exactly that, with areas of maximum constructive interference forming the elevated squares and areas of maximum destructive interference forming the depressed ones. The grid spacing, the distance between the elevated peaks, is determined by the wavelengths of the two swell systems and the angle between them. A narrower angle produces a grid with larger cells. A wider angle, approaching 90 degrees, produces a tighter, more violent grid with peaks that appear and disappear more rapidly. The critical phrase in that description is appear and disappear. Unlike single-swell waves, which have a consistent period and maintain their shape across large distances, the peaks in a cross-sea pattern are not stationary. They pulse. They appear, reach their maximum height, and collapse in a fraction of the time it takes a regular swell to pass. This has a direct and devastating consequence for ship stability. The conventional technique for managing rough seas, turning the bow into the oncoming swell, provides almost no benefit in a cross sea because there is no single oncoming direction. The vessel is surrounded. The two swell systems responsible for a cross sea are individually, usually entirely navigable. A vessel capable of handling 3-meter seas in normal conditions can manage a 3-meter swell from the northwest and a 3-meter swell from the southwest with reasonable confidence, if it encounters them separately. But when they arrive simultaneously and their peaks happen to coincide beneath the ship's keel, the vessel is briefly lifted by 6 meters of water. That lift is not the problem. The problem is what happens a few seconds later, when the constructive interference peak has passed and both swells have moved into a trough phase simultaneously beneath the hull. The ship drops. Not gradually, as in a regular swell, but suddenly, into a void of water that, by the mathematics of superposition, is just as much lower than baseline as the peak was higher. The stress on the hull during that drop, combined with the rotational forces imposed by waves arriving from two different directions, is not something marine architects have historically designed for, because historically, the assumption was that dangerous wave energy came from one primary direction at a time. The wavelength relationship between the two swell systems also governs the temporal distribution of these peak events. If the two swells have similar wavelengths, say, a primary swell of 250 meters and a secondary of 220 meters, the peaks will align at regular, predictable intervals. But if the wavelengths are substantially different, the constructive interference events become irregular and almost impossible to anticipate. A crew might experience 10 minutes of manageable conditions, then a single, violent peak with no warning, then another extended period of relative calm. In open ocean conditions, these irregular peak events are often recorded in ship logs simply as rogue waves, because they emerge from what appears to be relatively calm water. Some rogue wave events are not rogue at all. They are cross-sea peaks, and the distinction matters because the appropriate response is entirely different. The angle between the two swell systems is generated, most commonly, by two distinct meteorological events. The dominant swell, usually the longer, more powerful one, originates from a major storm system, a depression churning hundreds of kilometers away and sending its energy outward in all directions. The secondary swell typically arises from a different source. Another storm system further away, local wind generating its own surface chop, or, in certain complex sea environments, the reflection of the primary swell off a coastline or underwater topography that refracts the energy back across the wave field at a new angle. This last mechanism, wave refraction generating a secondary system from the primary, means that cross seas can develop in waters where only one storm system is active, provided the local geography creates the right angle of return. The waters around islands and headlands are particularly prone to this. The most reliable cross-sea zones in the world ocean are produced by the intersection of long-fetch trade wind swells with local or regional storm swells arriving from higher latitudes. The Canary Islands, the Azores, the waters north of New Zealand, the zone between the South African Cape and the Antarctic convergence. These are places where prevailing swell directions from distant, powerful, and reliable storm tracks collide with secondary systems arriving at consistent angles. They appear on the charts of experienced ocean sailors not as labeled hazards, but as experience-transmitted warnings. The old expression, confused seas, in ship logs from these regions carries, for those who know what to look for, the specific implication of cross-swell interference. The geometry of colliding oceans is not chaos. It is mathematics made liquid. And the terrifying thing about mathematics is that it arrives whether you are ready for it or not. A cross-sea does not require a hurricane. This bears repeating, because the natural tendency when imagining a sea state capable of sinking large ships is to populate the mental image with dramatic meteorology, towering storm cells, violent squalls, the kinds of visible atmospheric fury that at least provides warning. Cross seas can form, and frequently do form, in weather that a casual observer would describe as pleasant, partly cloudy, a light breeze. The kind of afternoon that appears in coastal tourism photographs. To understand why, it is necessary to follow the biography of a wave from its birth. Wind generates ocean waves through a process of energy transfer that begins at the molecular level and builds, over time and distance, into swells capable of crossing entire ocean basins. The initial mechanism is aerodynamic. Wind moving over a flat water surface creates tiny pressure differences that produce barely perceptible ripples, called capillary waves, just a few centimeters long. As wind continues to blow, these ripples offer more surface area for the wind to act upon, which increases the energy transfer, which makes the waves grow. The longer the wind blows in a consistent direction, and the greater the expanse of open water over which it acts, the technical term is fetch, the larger and longer the waves become. A storm with sustained winds of 70 kilometers per hour blowing across 2,000 kilometers of open ocean will generate swells that can survive for days and travel thousands of kilometers beyond the storm's position. The crucial characteristic of these mature swells is their organization. In the immediate vicinity of the generating storm, the wave field is chaotic, waves of many different sizes and periods tumbling over each other in what sailors call wind sea, a steep, confused, uncomfortable surface. But as the swells propagate away from the storm, they organize. Longer wavelength swells travel faster than shorter ones, a fundamental property of ocean waves in deep water called dispersion, and so the wave field sorts itself by period as it spreads. What arrives at a distant coastline from a far-off storm is not the chaos of the storm itself, but a series of clean, organized swell trains, longest period first, each representing a different moment in the storm's energy output. By the time these swells have traveled 5,000 kilometers, they are remarkably regular, predictable, and powerful, capable of producing heavy surf on beaches with no cloud in sight. Now two of these swell systems from two different storms in two different parts of the ocean arrive simultaneously at the same stretch of water. This is not unusual. It is, in fact, the normal state of affairs in the open ocean. The North Atlantic in any given week might be processing swells from a Canadian maritime depression, a subtropical system near the Azores, and residual energy from a storm that peaked near Iceland 4 days earlier. The Southern Ocean, which produces some of the longest and most powerful swells on Earth, routinely drives multiple swell trains northward at angles dictated by each system's track across the polar latitudes. The Pacific, the largest ocean basin, can carry swells from storms as far apart as the Aleutian Islands and the waters south of New Zealand simultaneously. Most of the time, when these systems coexist in the same stretch of water, the angle between them is small enough, or the energy of one system is great enough to dominate the other, that the resulting sea surface, while complex, does not produce the regular, grid-like interference of a true cross sea. The critical threshold is that divergence angle. When two swell systems arrive at angles roughly 60 degrees or greater to each other, the grid pattern begins to emerge. Below 60 degrees, the interference pattern smears into a longer, more complex swell shape that is uncomfortable and potentially dangerous, but does not produce the sharp, rapidly appearing and disappearing peak events that characterize cross-sea conditions. The atmospheric chain of events most likely to produce a severe cross-sea begins with two storm systems developing in relative proximity, but at angles that will direct their swell energy along diverging paths. In the North Atlantic, a classic setup involves a deep low-pressure system tracking northeast across the central basin, generating a primary swell directed toward Western Europe, while simultaneously a secondary low develops to the south of Iceland and sends its energy southeast, directly into the path of the primary swell, at a near-perpendicular angle. Neither storm needs to be exceptional. The swell energy they generate, even from relatively modest systems, will organize, propagate, and intersect at whatever geographic point lies in both systems' paths. The surface expression of cross seas also varies significantly with the relative energies and wavelengths of the two systems. When both swell trains carry similar energy and similar wavelengths, the grid pattern is nearly symmetrical, peaks and troughs of roughly equal magnitude, appearing and disappearing with regular spacing. This is paradoxically, the most visually spectacular but not necessarily the most dangerous configuration, because the peak events are distributed evenly, and a vessel caught in the pattern has statistically similar encounters from all directions. More hazardous in many ways is the asymmetric cross-sea, where one swell system carries significantly more energy than the other, producing a wave field that looks, from the surface, like a disturbed but recognizable swell pattern, with irregular peaks appearing to punctuate it. These irregular peaks, the moments of constructive interference between a dominant and a subordinate swell, are harder to visually distinguish from the dominant swell, providing less visual warning before a significant peak event arrives under the hull. The temporal scale on which cross seas develop and dissipate is also not governed by the local weather. A cross-sea pattern can persist for hours or days after both generating storm systems have weakened or moved away, because the swells themselves carry their energy independently of the weather that created them. Conversely, the conditions in which a ship encounters a cross-sea may be thoroughly benign at the local level: fair skies, light winds, moderate air temperature, while the wave field represents the intersection of storm systems that peaked days earlier and hundreds of kilometers distant. This decoupling of sea state from local weather is one of the principal reasons cross seas are underrepresented in danger assessments. When an officer looks at the barometer and the sky and sees calm conditions, the instinct is to relax. The swells, already in motion from distant causes, are indifferent to the barometer. There is one additional mechanism for cross-sea formation that deserves specific mention: the interaction between swell and current. Where powerful ocean currents run contrary to an incoming swell, the Agulhas Current off the southern tip of Africa is the classic example. A fast, warm river of water running southwest into South Atlantic swells running northeast. The current compresses the wavelength of the opposing swells, steepens their faces, and can dramatically amplify the energy released in interference events. The Agulhas has a documented history of rogue wave production that is partially attributable to this mechanism and the interaction between swell seas. Thames and strong countercurrents is now understood to modulate the severity of cross-sea events in ways that the wave field alone would not predict. A cross-sea in a strong opposing current is a cross-sea wearing amplifiers. In March of 1978, the supertanker Amoco Cadiz ran aground off the coast of Brittany, releasing 1.6 million barrels of crude oil in what remains one of the worst marine pollution events in history. The proximate cause of the grounding was a steering failure, later traced to a hydraulic fault in the rudder system. But marine accident investigators noted something in the preliminary conditions. In the hours before the hydraulic failure, the Amoco Cadiz had been navigating a complex sea state in the waters off Brittany, waters that, as subsequent analysis would confirm, are among the most prone to cross-sea interference patterns in the northeastern Atlantic. The rudder system's hydraulic components were under repeated, irregular loading cycles inconsistent with the prevailing swell conditions. They were being asked to work in directions the engineering had not anticipated. No one characterized the conditions as a cross sea in the accident report. The terminology was not yet standardized, the phenomenon not yet clearly defined as a distinct sea state. But the physical signature was there: irregular, non-directional wave loading on a vessel that, like every vessel of its type, was designed to handle force along its longitudinal axis. The structural physics of what cross seas do to ships begins with a concept called hull bending moments. A ship is, from an engineering standpoint, a beam, an elongated structure subject to bending forces along its length. When a single swell runs parallel to a ship's beam, the vessel hogs. The wave lifts the bow and stern while the midship section hangs unsupported, bending the keel upward in the center. When the wave crest passes under the midship section, the vessel sags. The center is supported while the ends hang, bending the keel downward at center. Hogging and sagging are designed for stresses. Every large vessel has explicit structural specifications for the maximum bending moments it can absorb, and those specifications are derived from the expected behavior of regular swell seas, one primary stress direction at a time. A cross sea does not offer one primary stress direction. It offers at least two simultaneously, and potentially more in the presence of local wind chop. A vessel caught in a cross-sea pattern is subject, at any moment, to a longitudinal bending moment from the primary swell and a transverse bending moment from the secondary swell. And at the moment of constructive interference, when a peak event lifts one corner or section of the hull disproportionately, the bending moments combine into torsional stress, a twisting force applied diagonally along the hull. Torsional stress is not something that conventional ship structural design has historically prioritized, because it is not a primary failure mode in single-swell seas. The consequences of this torsional loading show up in specific patterns of structural failure. Hatch covers and deck openings, which are areas of reduced rigidity in the hull structure, are particularly vulnerable. The twisting motion concentrates stress at their corners, and in severe conditions, the sealants and structural members around them can fail, allowing water ingress from above at the same time the hull is being worked below. The deck plating itself can develop cracks in the diagonal stress planes, not the clean transverse breaks that hogging might produce, but the jagged, unpredictable cracks that propagate at 45-degree angles across the hull plating, following the principal stress directions of a torsional load. Historical ship loss records, analyzed in the 1990s and 2000s by Padraic O'Brien and colleagues at University College Cork, and by researchers at the Technical University of Hamburg, revealed that a statistically significant proportion of large vessel losses in certain ocean regions showed structural failure patterns consistent with torsional loading rather than single-axis bending, losses that had been previously attributed to rogue waves, equipment failure, or human error. The roll behavior of ships in cross seas is the other major threat vector, and in some respects the more immediately lethal one. A ship's stability, its tendency to return to upright after being heeled by wave action, is characterized by what naval architects call the righting moment curve, the relationship between angle of heel and the restoring force the ship generates to return to vertical. Every ship has a roll period, a natural frequency at which it tends to oscillate when healed, determined by its mass distribution and its righting moment curve. In regular single-swell seas, a skilled navigator can modulate the ship's speed and heading to avoid synchronous rolling, the dangerous condition in which the ship's natural roll period m matches the swell period, and each successive wave drives the roll to a larger angle. In a cross-sea, synchronous rolling with one wave system is almost impossible to prevent, because avoiding it with the primary swell often brings the vessel into resonance with the secondary. But the more dangerous phenomenon is what engineers call parametric rolling, and cross seas are exceptionally efficient at generating it. Parametric rolling occurs when a vessel's stability varies rhythmically with the wave period, specifically when the wave crests, which have different buoyancy characteristics than the troughs, pass under the ship in a way that periodically reduces the righting moment. In cross seas, the pulsing, grid-like peak events can reduce a ship's effective stability dramatically, and then restore it within seconds, producing rapid, large-amplitude rolls that do not require the ship to be oriented broadside to the waves. Parametric rolling was identified as a primary factor in the loss of the car carrier, MSC, Napoli off the English coast in 2007. And while that vessel was in an unusually severe storm, parametric rolling events have been recorded in cross-sea conditions at wave heights that would not normally be considered threatening. The cumulative fatigue dimension is, over longer time scales, perhaps the most insidious consequence of cross-sea exposure. Metals fail not only under single extreme loads, but under repeated moderate loads. This is the phenomenon of fatigue cracking, well understood in aerospace and civil engineering, somewhat less systematically addressed in ship structural design until the late 20th century. A vessel crossing a cross-sea region for 6 or 8 hours is subject to thousands of small torsional, bending, and twisting load cycles, each individually well within the hull's design envelope, but collectively accelerating the propagation of microscopic cracks in the steel. These cracks propagate silently, invisible to standard inspection, until they reach a length at which a single severe load event, which might be entirely survivable in an undamaged hull, causes a catastrophic fracture. This is the mechanism that investigators believe contributed to the loss of the MV Derbyshire in 1980. A bulk carrier that disappeared in the Western Pacific with all 24 crew members, and whose wreck, found in 1994 on the floor of the Pacific Ocean at 4,200 meters, showed fracture patterns inconsistent with simple storm flooding. The hull had broken in ways that suggested a structural compromise preceding the final sinkage. The cross-sea breaks ships through methods that are individually survivable and collectively lethal. It is the mechanism of 1,000 moderate blows rather than a single decisive one, and it operates in conditions that, by every visual and meteorological indicator, a competent mariner would not identify as extreme. At 47 degrees north, 7 degrees west of the French coast, there is a stretch of ocean where the Atlantic swell meets the Bay of Biscay in a perpetual argument about direction. The Isle de Ré area has been documented as a cross-sea location in scientific literature since the 1990s, when French oceanographers first identified the recurring interference pattern, using the wave rider buoys that the French National Meteorological Service, Météo France, had deployed along the Atlantic coast. Those buoys recorded wave spectra, not just significant wave height, but the directional distribution of wave energy. And what they showed was not a single dominant swell arriving from one direction, as the models had assumed, but two distinct swell trains arriving at angles between 60 and 90 degrees to each other, recurring with sufficient frequency that the cross-sea pattern had to be considered a baseline feature of the region rather than an anomaly. This distinction, baseline feature versus anomaly, is the one that matters most for maritime risk assessment. A cross-sea that occurs once every several years in a given location is a hazard. A cross-sea that occurs several times per year, reliably in the same geographic area, is a maritime characteristic that defines the risk profile of that entire region. And the global map of cross-sea territories reveals a pattern that aligns closely with two things: the geography of ocean current boundaries and the intersection of major storm track corridors. The waters around the southern tip of Africa form what many oceanographers consider the world's most intense cross-sea zone. The Agulhas Current, which flows southwest along the southeastern coast of Africa before turning sharply back on itself, a phenomenon called the Agulhas retroflexion, creates a zone where powerful southwesterly swells generated in the Southern Ocean encounter the current itself, the reflected swell energy from the retroflexion, and the locally generated wave fields from the frequent, intense low-pressure systems that track across the South Atlantic. The result is a wave field of exceptional complexity. The historical record of large vessel losses in the waters between Port Elizabeth and Durban, what maritime historians sometimes call the Agulhas death zone, includes dozens of vessels that disappeared or were found badly damaged with no weather conditions severe enough to explain the losses under conventional single-swell sea state assumptions. The stretch is now known to generate rogue waves more reliably than almost any other location in the world ocean. And while not all of those rogue events are pure cross-sea constructive interference peaks, cross-sea mechanisms contribute significantly to their generation. The North Atlantic maintains several persistent cross-sea zones. The waters south and west of Iceland, where the prevailing North Atlantic swell from Canadian maritime storms intersects the locally generated swell from Icelandic atmospheric systems, produce cross-sea conditions that are well documented in the logs of fishing vessels and ferries that operate in that region year-round. The Denmark Strait between Iceland and Greenland is particularly complex. The interaction of the East Greenland Current with the Erminger Current creates a zone where the oceanographic forcing on swell propagation adds to the meteorological generation of crossing swell systems. The Faroe Islands sit in a region where cross-sea patterns can develop even in what regional weather forecasts describe as moderate conditions, because the swell fetch from two different storm regions can simultaneously target the Faroes from angles that produce interference. In the Pacific, the zone west of Hawaii is a documented cross-sea region, where the dominant North Pacific swell from Aleutian storms intersects the easterly trade wind swell generated across the tropical Pacific. The waters around Japan, particularly the zone between Honshu and the Kuril Islands, are subject to complex cross-sea interactions driven by the intersection of Pacific swell systems with the locally generated seas of the frequent and intense Northwest Pacific cyclones, the region that produces more typhoons than any other area of ocean. The waters west of the Kamchatka Peninsula and the Sea of Okhotsk have a particularly dangerous seasonal cross-sea signature in autumn, when typhoon remnants drive swell northward into the zone, already receiving westerly swell energy from Pacific storms. The Indian Ocean presents a different cross-sea geography, driven by the monsoonal reversal that switches the dominant wind and swell direction twice annually. During the southwest monsoon, the Arabian Sea receives powerful swell energy from the vast fetch of the Indian Ocean. During the northeast monsoon, a different swell system dominates. In the transition periods between these regimes, the changeover, months of April-May and October-November, the two competing swell systems can coexist in the Arabian Sea for weeks, creating persistent cross-sea conditions across an area that carries an extraordinary density of commercial shipping between the Persian Gulf and the major Asian economies. The specific zone between Sri Lanka and the Maldives has been identified in wave spectra data as particularly prone to cross-sea development during the intermonsoonal periods. The common thread through all these regions is the intersection of two reliably present swell sources, not two random storms, but two climatological swell-generating mechanisms that are predictable enough to produce crossing conditions with seasonal or regional regularity. Ocean swell climate, the long-term average direction, period, and energy distribution of swells in a given area, is now mapped in sufficient detail that oceanographers can identify not just where cross seas have occurred historically, but where they are structurally likely to occur based on the wave-climate intersection geometry. What is striking when these maps are assembled is how many of the world's most heavily trafficked shipping routes run directly through documented or structurally predicted cross-sea territories. The South African route between Europe and Asia, before the expansion of the Suez Canal made the route through the Red Sea economically dominant, was notorious precisely because it ran through Agulha's cross-sea territory. The northern European routes between major Atlantic ports pass through the North Atlantic cross-sea zones near the Faroe Islands and Iceland as a matter of geography. The Trans-Pacific routes connecting Asia with the American West Coast cross the zone west of Hawaii, where cross-sea conditions are climatologically embedded in the spring swell pattern. These are not rare excursions into hazardous waters. These are the normal routes, run thousands of times per year by vessels whose routing algorithms are optimized for fuel efficiency and schedule compliance, with wave avoidance criteria based primarily on significant wave height, a metric that does not capture the directionality that determines W. Whether a given wave field is a manageable regular sea or a cross sea with lethal potential. On the morning of January 3, 1998, The fishing trawler Han Bol was returning to the Danish port of Thyboron through the northern approaches to the Skagerrak, the passage between Norway and Denmark that connects the North Sea with the Kattegat. The sea state that morning was later measured at significant wave heights of between 3 and 4 meters, uncomfortable but entirely within the operational envelope for a vessel of that type. The crew, 4 experienced fishermen, knew the Skagerrak the way a driver knows a familiar road. What they did not know was that a secondary swell system from a Norwegian coastal storm was intersecting the North Sea swell at an angle of approximately 72 degrees in the precise stretch of water they were crossing. The boat was later found drifting without power about 12 kilometers from its last known position. One crew member was found on deck with a broken collarbone and several broken ribs. The other 3 were never recovered. The survivor reported when he regained consciousness in the hospital that the boat had been struck from below at an angle, that it had felt not like a wave but like a road bump traversed at speed. A brief peak event in a moderate cross sea, for a moment indistinguishable from the surrounding water, had lifted one corner of the hull hard enough to throw 3 men into the January Skagerrak. The physiology of what human bodies experience in cross-sea conditions begins with the vestibular system, the balance mechanism housed in the inner ear, which processes acceleration signals to determine which way is down and how the body is moving. In a regular swell sea, the vestibular system receives rhythmic, predictable signals, a gradual pitch forward and back as the bow rises and falls, a gentle roll as the ship heels and recovers. Experienced sailors adapt to these signals and find them tolerable, even soporific. Their bodies learn the rhythm. They brace at the right moments, relax in the troughs, move around the vessel with a compensatory adaptation that keeps them upright without conscious effort. A cross sea provides the vestibular system with inputs for which human evolution has left no preparation. The pitch and roll arrive simultaneously from different axes, changing in magnitude and direction with no pattern that the nervous system can extract. The semicircular canals, the 3 fluid-filled loops in the inner ear that detect rotation, receive signals in all 3 planes simultaneously and irregularly. The result, in almost all humans regardless of sea experience, is the immediate onset of severe motion sickness. But motion sickness, while incapacitating, is not the primary danger. The primary danger is what happens to the body when the cross sea produces its sudden, irregular peak events. When the constructive interference peak of a cross sea appears beneath a vessel, the upward acceleration can be sudden enough, occurring in 1 to 2 seconds for a moderate peak event, to produce what engineers call impulsive loading on everything the ship carries, including its human occupants. At the moment of peak lift, a person standing on a deck is suddenly heavier than normal. A 60-kilogram crew member might momentarily weigh 80 or 90 kilograms as the upward acceleration adds to gravitational loading. This is uncomfortable but manageable. The dangerous moment is the reversal, when the peak has passed and the vessel falls into the subsequent trough. The downward acceleration can produce, for a fraction of a second, a state approaching weightlessness. Hands and feet holding railings, ropes, and handles find that the body they were anchoring is suddenly lighter than expected. Feet lose contact with decks. Crew members who were standing are briefly airborne, and when contact with the deck resumes, sometimes 2, sometimes 3 seconds later, in a vessel that has rotated its deck plane because of the secondary swell component, the body makes contact with a surface at an angle and a velocity that causes injury. Maritime injury statistics from vessels operating in complex sea states show a specific pattern of injury consistent with these dynamics. Fractures of the wrist, forearm, and clavicle, injuries consistent with arms thrown out to break a fall, combined with spinal compression injuries consistent with vertical loading at the moment of contact with a surface. These are distinguishable from the bruise and laceration injuries that result from being struck by equipment or fallen objects in single-swell rough weather. They are the injuries of people who have been briefly airborne and who have landed badly, and they are disproportionately represented in cross-sea accident records relative to regular storm sea records. The psychological dimension of cross-sea exposure is less well documented than the physiological one, but the anecdotal evidence from survive. Ours is consistent. The absence of rhythm, the inability to anticipate the next significant motion, is reported as uniquely exhausting and disorienting. Experienced seafarers describe cross-sea conditions as wrong in a way that severe but regular storm seas are not. Regular storms can be terrifying, but they are comprehensible. The water is doing something recognizable, something the body and mind can partly adapt to. Cross seas violate the sailor's developed intuition about wave behavior without providing a replacement pattern. The result is a sustained, unrelenting state of hypervigilance that exhausts the human nervous system in ways that regular storm conditions do not. Sleep becomes almost impossible in severe cross-sea conditions, not just because the irregular motion makes lying down precarious, but because the nervous system cannot find a baseline from which to relax. Crews operating in cross-sea conditions for extended periods report cognitive degradation, slower response times, worse judgment, reduced manual dexterity. That begins to parallel the effects of significant sleep deprivation within 12 to 18 hours. A crew that is simultaneously seasick, physically battered by irregular peak events, and cognitively compromised by sleeplessness is a crew increasingly unable to make the precise, coordinated decisions that navigating a cross-sea environment actually demands. The accumulation of these factors, physiological loading, injury risk, motion sickness, and cognitive degradation, helps explain why cross-sea accidents so often involve decisions that, in retrospect, seem avoidable. A crew in good condition in a regularly rough sea can make the decision to alter course, reduce speed, deploy sea anchors, or call for assistance with the clear-headed judgment these decisions require. A crew that has spent 8 hours in a cross sea is frequently operating well below peak capacity at precisely the moment when the sea state demands something above it. The human body, like the steel hull it occupies, was not designed for the grid of water. It was designed by millions of years of evolution for rhythms, the rhythm of the seasons, the rhythm of day and night, the rhythm of footfall on solid ground. The cross sea offers it none of these courtesies. In the summer of 1994, the World Meteorological Organization convened a working group in Geneva to discuss a problem that had been quietly accumulating in the wave forecasting community for nearly 2 decades. Operational wave models, despite steady improvements in their underlying physics and computational power, were producing systematic errors in certain sea states. Not errors in significant wave height, the overall measure of how rough the sea was, but errors in the wave spectrum, the distribution of energy across different wave periods and directions. The models were, in some environments, substantially underestimating the amount of wave energy arriving from secondary directions. They were not seeing the full picture. And the sea states where this underestimation was worst were precisely the conditions in which cross seas developed. The history of ocean wave forecasting is, in many respects, a history of gradually recognizing the limitations of simplification. The first modern operational wave forecasting methods, developed in the 1950s by Harold Sverdrup and Walter Monk working from British Admiralty data, were essentially one-dimensional. They modeled the growth of wave energy under a given wind field and its propagation to a given point, treating the wave field as a single system with a dominant period and direction. This was sufficient for the specific problem they had been asked to solve, forecasting surf conditions on beaches in preparation for amphibious military landings. But it was always understood to be an approximation. The real ocean never presents a single wave system. The development of spectral wave modeling in the 1970s and 1980s, culminating in the establishment of the WAVEWATCH-III model at the U.S. National Oceanic and Atmospheric Administration, and the WAM, Wave Action Model, maintained by the European Center for Medium-Range Weather Forecasts, brought wave forecasting closer to the physics of the real ocean by treating the wave field as a continuous spectrum of energy distributed across many periods and directions simultaneously. This was conceptually correct. The implementation, however, was constrained by the computational resources available at the time, which required discretization of the directional spectrum into a finite number of angular bins, typically 24 or 36 directions, and a finite number of frequency bins. Energy arriving at angles between bins was spread across the adjacent bins in a process called numerical diffusion that, in certain directional configurations, substantially underestimated the sharpness and energy of narrowly focused secondary swell systems. The specific problem for cross-sea prediction, W, as that secondary swell systems, particularly those generated by distant storms and therefore highly organized in their directional energy, fell between the directional bins of the model in ways that spread their energy artificially, reducing the apparent energy at any given angle and preventing the model from correctly identifying the two-swell system structure that was the physical basis of the cross-sea condition. The models, in essence, could not distinguish a true cross-sea from a slightly confused single-swell sea, because their angular resolution was insufficient to represent both swell trains simultaneously with their actual directional sharpness. This was not a small error. The wave spectra recorded by moored buoys in documented cross-sea zones showed directional peak widths that were sometimes as narrow as 15 to 20 degrees, narrower than the directional resolution of the operational models of the era. An organized distant swell arriving from precisely southwest-southwest was in the model partially registered as arriving from south and partially from southwest and partially from west, with the peak energy at no single direction appearing significant enough to trigger cross-sea warnings. Meanwhile, the buoy was measuring two perfectly distinct swell trains, separated by 78 degrees, both carrying enough energy to produce the interference pattern that the model had in effect averaged away. The improvement of wave model directional resolution was steady through the 1990s and 2000s. Modern operational models run with directional resolutions of 10 to 15 degrees, a substantial improvement. But the fundamental challenge of representing sharply peaked swell systems in a discretized directional spectrum was never fully resolved. More importantly, the operational products delivered to mariners from these models, the wave forecasting bulletins, the wave height charts, the ship routing guidance, continued for decades to report only significant wave height and dominant wave period and direction. Single-number summaries of what was, in reality, a multi-peaked directional spectrum. A wave height chart showing 3-meter seas does not distinguish between 3 meters of organized single-swell sea and 3 meters of significant height in a two-system cross-sea configuration. For ship routing and risk assessment purposes, these are radically different sea states. The chart treated them as identical. The practical consequence of this forecasting gap was a systematic inability to warn mariners of cross-sea conditions until they were already in them. A vessel routing itself through the North Atlantic based on wave height charts alone, which was, until the late 2000s, essentially universal practice for commercial shipping, had no tool available to it that would identify the approach of a cross-sea condition in a given area, unless the significant wave height in that area was already high enough to appear as a routing hazard. Moderate but perfectly organized cross-seas, generating dangerous conditions at wave heights of 2 to 4 meters, were invisible to the routing process. The academic recognition of this gap preceded practical improvements by roughly 15 years. A landmark paper by Peter Jansen at ECMWF in 2003, followed by work from Mark Dolman at the University of Miami, and subsequent contributions from research groups in France, Germany, and Australia, quantitatively demonstrated the relationship between sea state bimodality, the technical term for a wave spectrum with two distinct energy peaks at different directions, and the probability of hazardous wave events. This work established, on a firm mathematical basis, what experienced mariners had known empirically for centuries. The dangerous sea is not always the high sea. It is sometimes the geometrically complicated sea, the sea whose danger is in its structure rather than its magnitude. The gap between academic recognition and operational implementation, between papers demonstrating the problem and forecasting products, that communicated it to ship masters, stretched across the first decade of the 21st century. The turning point, at least in research terms, came with the development of dual-peaked wave spectrum detection algorithms that could be applied to the output of spectral wave models to automatically identify sea states with two distinct directional energy peaks. These algorithms, implemented experimentally at Météo France, at the UK Met Office, and in the NOAA Wave Modeling Division, could flag grid points in the global wave model domain where the model output showed the signature of a cross-sea configuration, even when the individual significant wave heights at those points were moderate. In principle, this was the technical foundation for cross-sea specific forecasting, not a separate forecast product, but a flag or warning layer added to existing wave height guidance that would alert mariners to the presence of a dual swell. L structure. In practice, the implementation of these algorithms into operational forecasting products has been, as of the present decade, partial and inconsistent. Some national meteorological services include cross-sea flags in their wave spectral products for coastal waters. Offshore waters, which are the domain of commercial shipping and where the majority of cross-sea ship losses occur, are less consistently covered. The International Maritime Organization's wave forecasting guidelines were updated in 2015 to acknowledge the hazard of bimodal sea states and recommend that mariners consult directional wave spectra rather than relying solely on significant wave height. But the wave spectral data necessary to follow this recommendation requires specialized software to interpret and is not routinely available on ship bridges in the format that a working officer can quickly assess. The tools that could not see the cross-sea are slowly, imperfectly, being replaced by tools that can. But the gap between what the science knows and what the mariner on the bridge can access, in a form usable under the time pressure of an active navigation situation, remains substantially unresolved. On New Year's Day, 1995, the oil platform Draupner in the North Sea recorded a wave with a crest height of 18.5 meters, more than twice the significant wave height of the surrounding sea state, which was estimated at approximately 12 meters. The instrument that recorded it was a downward-looking laser altimeter mounted on the platform's lower deck, designed primarily for structural monitoring. The recording was automatic, unattended, and produced a single data trace on a strip chart recorder that was not examined until the following morning. When engineers reviewed it, the trace showed an unmistakable spike, a sharp, narrow peak towering above the surrounding record of irregular but individually unremarkable waves that lasted for approximately 20 seconds before returning to the level of the background sea. The Draupner wave, as it came to be known, became the first instrumentally confirmed rogue wave in the scientific literature. The first unambiguous measurement of a wave that violated the distribution of heights that standard wave physics, based on the mathematics of a single swell system, predicted. The Draupner wave did not emerge from calm water. The sea state that New Year's Day was already rough by anyone's standard, but its recorded height of 25.6 meters from trough to crest was, in a significant wave height of 12 meters, a wave that the prevailing models said should occur, at most, once every 10,000 years in that sea state. Analysis published later, including a definitive study by Paul Taylor and colleagues at the University of Oxford in 2011, concluded that the Dropner wave was most likely produced by constructive interference between two crossing swell systems, that the North Sea on that day had the bimodal spectral signature of a cross-sea, and that the Dropner wave was a cross-sea peak event, albeit an exceptionally large one. This was significant not because it explained one wave event, but because it suggested a mechanism by which rogue waves, defined as waves exceeding twice the significant wave height of the surrounding sea, could arise with far greater frequency than standard single-spectrum wave theory predicted, and in conditions recognizable in advance from the wave spectral signature. The mathematics of superposition do not just produce the regular grid pattern visible in cross-sea photographs. They produce a statistical distribution of wave heights that has a longer tail than the Gaussian distribution that applies to single-spectrum seas. More moderate peaks, yes, but also more extreme peaks, appearing more often, scattered unpredictably through the wave field rather than arising from a single, identifiable location or direction. The statistical link between cross-sea sea states and elevated rogue wave probability was quantified in the work of Miguel Honorato at the University of Turin, whose group published a series of papers between 2006 and 2012 demonstrating that the probability of a rogue wave event in a given sea state scales strongly with the directionality of the wave field. Narrow-banded, single-direction swell produces the lowest rogue wave probability. Broad-spectrum, multi-direction sea states, of which cross seas are the most extreme example, produce substantially higher rogue wave probabilities. The mechanism identified in Honorato's numerical simulations and laboratory experiments was not simple linear superposition, but a more complex nonlinear interaction between wave components that becomes significant at larger wave steepnesses. A second-order effect, technically called quasi-resonant four-wave interaction, that selectively amplifies the largest waves in a bimodal spectrum beyond what linear superposition alone would predict. This means that cross seas are not just dangerous because of the id pattern of moderate constructive interference peaks visible in satellite photographs. They are dangerous because the specific spectral configuration of a cross-sea, two distinct, energetic swell trains at a large angle, is precisely the configuration in which the rogue wave probability is maximized by the nonlinear physics of ocean waves. The visible grid is, in some sense, the relatively benign manifestation of a cross-sea. The rogue peak events, appearing without the regular spacing of the grid, arising from nonlinear amplification rather than simple geometric interference, are the extreme tail of the distribution that the same physical configuration produces. The satellite imaging of ocean wave fields, which became scientifically useful in the 1990s, with the deployment of synthetic aperture radar instruments on European and Canadian Earth observation satellites, provided the first systematic global view of cross-sea patterns. Synthetic aperture radar, SAR, is sensitive to the roughness of the ocean surface at spatial scales that correspond to the wavelengths of ocean swells, and its two-dimensional imaging capability means that it can, unlike a buoy, simultaneously image the directional structure of the wave field over an area of hundreds of square kilometers. Analysis of SAR imagery archives by groups at the European Space Agency and at the German Aerospace Center revealed, in studies published in the early 2000s, that cross-sea patterns were visible in the SAR record far more frequently than the sparse buoy network had suggested. Roughly 17% of SAR ocean images showed evidence of bimodal wave spectra consistent with cross-sea conditions, with higher frequencies in the documented cross-sea zones and lower, but non-zero, frequencies in regions previously assumed to have simple swell climates. The 17% figure is striking. It means that in any given snapshot of the world's major ocean shipping routes, roughly 1 in 6 shows a wave field configuration that substantially elevates rogue wave probability above the level assumed in conventional ship design and routing practice. Ship structural design standards, as maintained by classification societies such as Lloyd's Register, Bureau Veritas, and DNVGL, use return period statistics for extreme wave events that are derived from single-spectrum wave height distributions. If cross-sea conditions elevate rogue wave probability significantly above those distributions, and the mathematical evidence suggests they do, then ship structures certified as adequate for expected wave loads in a given trade route may be systematically underdesigned for the actual wave environment they encounter. The ghost peaks of cross seas, the large, rare, non-linearly amplified events that arise from the same spectral configuration as the visible grid, are the mechanism by which cross-sea conditions produce casualties that, in the absence of the spectral data needed to reconstruct the sea state, appear inexplicable. A vessel lost in a sea state with a significant wave height of 4 meters, with no storm conditions reported and no obvious mechanical failure, poses a classification problem in accident investigation. The cross-sea ghost peak, a single event lasting perhaps 30 seconds, towering briefly to 8 or 10 meters from a baseline of 4, striking the vessel from a direction inconsistent with the dominant swell, leaves no trace that conventional accident investigation tools can recover. The vessel is gone, the sea is back to normal, the ghost has passed through. The fundamental problem confronting naval architects who wish to design ships resistant to cross-sea damage is one of specification. You cannot design for a load case you cannot precisely define. Single-swell structural design rests on return period calculations. Given the wave climate of a specific trade route, what is the wave height exceeded, on average, once in 20 years, once in 100 years? The ship's structural envelope is then designed to handle the expected loads from waves in that range, with appropriate safety factors applied. This is rational engineering under conditions where the primary failure mode, hogging and sagging from longitudinal swell loading, is understood and quantifiable. Cross-sea loading does not fit neatly into this framework for 2 reasons. First, the probability of a given cross-sea peak event in a given location depends on the full directional spectrum of the wave field at that moment, not just the significant wave height. And operational wave climate statistics have historically been compiled in terms of significant wave height and dominant period, without adequate directional resolution to quantify cross-sea occurrence frequency. Second, the critical load case in cross-sea conditions. The torsional stress from simultaneous longitudinal and transverse wave loading is not the same load case as the extreme single-swell loads that structural design standards use as their reference. It is a different failure mode with a different statistical character, and incorporating it into design standards requires both the statistical data on cross-sea frequency and the structural analysis methodology to compute torsional loads accurately. Progress on both fronts has been made, beginning in earnest with the work of the International Ship and Offshore Structures Congress, ISSC, in the 2000s, which established working groups specifically tasked with quantifying the structural response of large vessels to bimodal sea states. The numerical tools for computing hull response to crossed wave systems, primarily finite element analysis models that can represent the three-dimensional deformation of a hull under simultaneously applied longitudinal and transverse wave loads, were available from the aerospace industry and adapted for marine use. What they revealed, when applied to standard large vessel hull forms, was that the torsional stresses produced in cross-sea conditions were, for certain hull proportions and cargo configurations, substantially larger relative to the hull's structural capacity than the classification society design standards had assumed. Container ships emerged as a particular area of concern. The container ship hull form, long, relatively narrow, with a flat, open deck interrupted by large hatch openings between the cargo bays, is geometrically well suited to carrying containers efficiently and poorly suited to resisting torsional loads. The large hatch openings reduce the effective torsional stiffness of the deck structure. Instead of a continuous box beam, the container ship hull is more like a series of ring frames connected by deck plating between the hatch openings, and the torsional stiffness of this structure is substantially less than that of a tanker or bulk carrier with a continuous closed deck. When cross-sea torsional loads are applied to a container ship hull in the finite element analysis, the stress concentrations at the corners of the hatch openings, the standard weak point of the structure, reach values that would not be predicted by hogging and sagging analysis alone. The response of classification societies to this evidence has been the gradual strengthening of hatch opening corner structural requirements and the development of more detailed torsional load analysis requirements for container ships of particular size ranges. The 2010s saw the introduction, by several major classification societies, of what are termed direct strength analysis, requirements for ultra-large container ships, vessels of 10,000 TEU capacity and above, that mandated explicit finite element analysis of the hull under combined bending and torsional load cases, rather than relying solely on the simplified beam theory calculations that had previously sufficed. This was a meaningful technical advance, but its application was limited to the very largest vessels and to new-build ships entering classification after the requirements took effect. The existing fleet, thousands of container ships of various ages and sizes, continued to operate under structural rules that had not incorporated cross-sea torsional loading as a primary design case. The roll damping question, how to reduce the amplitude of cross-sea induced parametric rolling, has generated a parallel track of engineering development. Passive roll stabilization systems, primarily bilge keels, flat plates welded along the bilge of the hull to increase hydrodynamic resistance to rolling, have been standard equipment on seagoing vessels for over a century. They are effective at reducing roll amplitudes in regular single-swell conditions. In parametric rolling conditions, where the roll is driven by the periodic variation of the ship's stability rather than by direct wave forcing, bilge keels provide reduced effectiveness because the roll is not being driven by the direct lateral force of the wave, but by the periodic reduction of the righting moment. The vessel is not being pushed over by a wave. It is periodically losing its ability to resist being heeled and recovering it in a rhythm that allows the roll angle to build cumulatively. Active stabilization systems, fin stabilizers that extend hydraulically from the hull and generate lift forces to oppose rolling, controlled by gyroscopic sensors that detect the onset of rolling and actuate the fins accordingly, perform better against parametric rolling than passive systems, but they require the control system to recognize and respond to the parametric roll signature, which is distinct from regular wave-forced roll. Control algorithms capable of detecting and specifically countering parametric roll were developed in the early 2000s and are now available as options on active fin stabilizer systems from major manufacturers. Their adoption on commercial vessels has been uneven, constrained by cost, and by the fact that insurance and classification requirements do not mandate them. The most promising recent development in cross-sea ship design is the application of computational fluid dynamics, CFD, to simulate, numerically, the interaction of a specific hull form with a cross-sea wave field. Where finite element analysis tells you whether a given load will break the hull, CFD tells you what the load actually is. How much force a cross-sea wave field of specified spectral characteristics will actually apply to a specific hull, in what direction, at what rate. The application of high-resolution CFD to cross-sea simulation requires substantial computational resources and has, until recently, been practical only for research purposes. The continuous improvement of computing hardware has made routine CFD cross-sea simulation progressively more accessible, and the leading ship design bureaus now routinely include cross-sea CFD analysis as part of the design validation process for large vessels intended for cross-sea territory trade routes. The ungovernable is being approached, gradually, through better tools, better rules, and better understanding of what it actually does to steel. At 780 kilometers above the ocean surface, a satellite moving at 7.4 kilometers per second can image a strip of ocean 400 kilometers wide. In the 12 minutes it takes to traverse a major ocean basin, Its synthetic aperture radar sweeps an area that no ship, no aircraft, and no array of buoys could survey in equivalent time. From this altitude, the cross sea is visible. The satellite does not feel the wave. It reads it in the microwave energy reflected from the roughened ocean surface, in the phase shift of radar pulses returned from swell crests moving toward or away from the sensor, in the two-dimensional pattern of backscatter intensity that, to a trained analyst, resolves into the paired directional peaks of a bimodal wave spectrum. The use of satellite-borne synthetic aperture radar for ocean wave observation began operationally with the European Space Agency's ERS-1 satellite, launched in 1991. ERS-1 carried an SAR instrument that was not primarily designed for wave observation. It was intended for land surface mapping and sea ice monitoring. But its ocean images quickly revealed that wave patterns were visible in the data at scales large enough to characterize the dominant swell systems present. The technique that emerged for extracting quantitative wave information from SAR imagery, converting the two-dimensional spatial pattern of radar backscatter into a two-dimensional wave spectrum, was developed by researchers at the Deutsches Klimmarzenzentrum and the Max Planck Institute for Meteorology in Hamburg, and by 1996, it was generating systematic wave spectral retrievals from the ERS-1 archive that revealed, for the first time, the global distribution of cross-sea conditions at a spatial and temporal density that the buoy network could never approach. The ERS-2 satellite, launched in 1995, and subsequently the ENVISAT mission of 2002, continued and expanded this observational record. Each new SAR mission improved the quality and quantity of wave spectral retrievals, and the accumulated archive through the 2010s became the empirical foundation for the statistical studies that quantified cross-sea frequency on a global basis. Researchers at the Ifremer Ocean Science Institute in Brest, France, particularly the group led by Fabrice Collard, published systematic analyses of SAR-derived cross-sea frequency that showed not just where cross-seas occurred, but how their frequency varied seasonally, how it correlated with the large-scale atmospheric circulation patterns that drive the swell climate, and how the major cross-sea zones mapped against ship traffic density. The result of overlaying cross-sea frequency with ship traffic density was not reassuring. The highest cross-sea frequencies in the global SAR record coincided with some of the world's most heavily trafficked ocean regions. The North Atlantic tracts between European and North American ports, the South African coastal routes, the approaches to the Strait of Malacca from the Indian Ocean side. The statistical cross-sea hazard was not distributed uniformly across remote ocean areas that ships occasionally traverse. It was concentrated in the areas that ships transit constantly. The Sentinel satellite series, launched by ESA beginning in 2014 as part of the Copernicus Earth Observation Program, represents the current state of the art in operational SAR ocean observation. The Sentinel-1A and Sentinel-1B satellites, operating in a coordinated constellation, provide repeat-pass SAR coverage of the global ocean at a frequency and geometric resolution substantially better than their predecessors. Crucially, the Sentinel SAR wave mode, a specific observation configuration optimized for wave spectral retrieval, generates data products that are processed in near real time and made freely available through the Copernicus Open Access Hub within hours of acquisition. This near real-time availability has, for the first time, made satellite-derived cross-sea spectral information potentially usable as an operational forecasting input rather than purely a research resource. The integration of satellite SAR wave data into operational wave forecasting through a technique called data assimilation, the statistical incorporation of observations into a running numerical model to correct its state estimate, was demonstrated in the 2010s by research groups at ECMWF and at NOAA's Environmental Modeling Center. SAR-derived wave spectra, when assimilated into the WAM or WAVWATCH III models, improve the model's directional spectrum estimate in the specific ways most relevant to cross-sea detection. The assimilation sharpens the directional energy peaks in the model output, reducing the numerical diffusion that had historically blurred the spectral signature of organized secondary swells. The improvement in cross-sea forecast skill from SAR data assimilation has been quantified in several studies as substantial, meaning that the assimilated model identifies cross-sea conditions with significantly better timing and spatial accuracy than the free-running model. The operational use of this technology, the actual integration of near real-time SAR wave spectra into the wave model runs that drive the marine weather guidance delivered to ship masters, has proceeded slowly. The computational infrastructure for real-time SAR data processing and assimilation is significant. The latency between satellite overpass and usable assimilated model output, while improved, remains in the range of 2 to 4 hours in the best operational configurations, adequate for strategic voyage planning, but marginal for tactical routing decisions made on time scales of 1 to 2 hours. The global SAR coverage, even with the Sentinel constellation, has gaps in time between overpasses over a given ocean area that can extend to 12 hours, meaning that rapidly developing cross-sea conditions between satellite passes are not captured in the observational record until after the next overpass. The solution being pursued in the research community is a hybrid approach. Satellite SAR for high-quality directional spectral snapshots, combined with dense wave buoy networks, wave-recording ships of opportunity, and improved physics in the wave models themselves, to reduce the directional diffusion that historically degraded cross-sea representation. Each component has limitations that the others partially compensate. The buoys provide continuous time series at fixed points but cannot see spatial structure. The ships of opportunity provide spatial coverage of high-traffic areas, but only measure the wave conditions at a single point along the ship's track. The models provide global spatial and temporal coverage, but with errors in the directional spectrum that the signatures in the global climate model ensemble, reproduced across dozens of independent modeling groups using different atmospheric codes, different ocean coupling schemes, different parameterizations of cloud and precipitation physics. As the atmosphere warms and the equator to pole temperature gradient shifts, a consequence of the Arctic warming faster than lower latitudes, the preferred latitudes at which mid-latitude cyclones develop, deepen, and track across the ocean basins are shifting poleward. In the northern hemisphere, the mean track of North Atlantic and North Pacific storm systems is moving northward by approximately 50 to 100 kilometers per decade, a shift that, accumulated over the course of the 21st century, represents a substantial geographic rearrangement of the principal swell-generating engine of the northern ocean basins. The implications for cross-sea geography follow directly from the geometry of swell propagation. The swell climate of any given ocean area, the prevailing directions, periods, and energies of the swells that arrive there, is determined by the location and intensity of the storm systems that generate them. When storm tracks shift, swell climate shifts. The angles at which swell trains from two different storm systems arrive at a given geographic location change as the source geometry changes. Areas that currently receive swell flow. M2 storm systems at an angle below the cross-sea threshold may, as storm tracks shift, begin receiving swell at angles that meet or exceed the threshold. Conversely, existing cross-sea zones may find their characteristic interference geometry disrupted as one or both of their source swell systems shifts direction. The quantitative prediction of future cross-sea geography is substantially more uncertain than the qualitative statement that it will change. The key uncertainty is not in the direction of storm track shift. The poleward movement is robust, but in the specifics of how the shift in storm track position translates into changes in the directionality of individual swell events at specific ocean locations. A storm track that moves 100 kilometers north generates a swell that arrives at a distant location from a direction roughly 1 to 2 degrees more northerly. The effect of this directional shift on the cross-sea probability at a given location depends sensitively on the current angles of the two swell systems and how close those angles are to the critical cross-sea threshold. The Southern Ocean, which generates the world's most energetic and far-reaching swells, is showing a trend distinct from the Northern Hemisphere storm track shift. An intensification of the westerly wind belt at high southern latitudes, associated with both the poleward temperature gradient shift and the Antarctic ozone hole recovery dynamics. The Southern Ocean swell climate is consequently shifting toward higher wave energy and slightly more southerly source locations for the most powerful swells. This shift is already measurable in long-term tide gauge and buoy records from Southern Hemisphere coastlines, which show increasing wave heights along the West Australian coast and the Pacific coast of South America that are attributable to the changing Southern Ocean swell climate. The consequences for the cross-sea geography of the South Atlantic and South Indian Ocean, where Southern Ocean swells intersect the locally generated swells of subtropical storm systems, have not been systematically analyzed, but are likely to produce regional changes in cross-sea frequency that the existing maritime risk framework is not prepared to anticipate. Sea surface temperature changes represent a second pathway through which climate change modulates cross-sea risk. Warmer sea surface temperatures in the tropical and subtropical Atlantic and Pacific provide more energy to tropical cyclones, which are intensifying, producing higher peak wind speeds and generating more energetic swells from lower latitudes. These tropical swell systems travel to higher latitudes and interact with the mid-latitude storm swells that have historically dominated the swell climate of most major shipping routes. The interaction between an intensifying tropical swell system and the existing mid-latitude swell climate changes the angular relationships between swell systems in ways that are not yet systematically characterized. The El Niño Southern Oscillation provides a template for understanding how large-scale ocean atmosphere variability modulates cross-sea geography on interannual timescales. During El Niño events, the position and intensity of the North Pacific storm track shifts substantially eastward, altering the directional distribution of North Pacific swell energy and consequently changing the cross-sea occurrence frequency in several Pacific Ocean areas. Wave model hindcasts, retrospective model simulations using observed atmospheric forcing, show elevated cross-sea frequency in the eastern North Pacific and reduced frequency in the western North Pacific during strong El Niño events, and the reverse during La Niña. The ENSO cycle provides, in this sense, a real-world demonstration that large-scale atmospheric changes produce detectable changes in cross-sea geography. If ENSO-scale atmospheric reorganization changes cross-sea geography on interannual timescales, then the multi-decadal atmospheric reorganization produced by greenhouse gas forcing will change it on timescales relevant to ship design, trade route planning, and maritime risk assessment. The insurance industry is watching this closely. Marine hull insurance, the financial product that covers ship damage and loss, is priced on historical loss records and actuarial models that assume the wave climate of the next 10 to 20 years resembles the wave climate of the past 10 to 20 years. If the wave climate is changing, if cross-sea occurrence frequency is increasing in some major shipping routes and decreasing in others, the historical loss record becomes a progressively less reliable guide to future risk. The Lloyd's Market Association, which represents the major London marine insurance underwriters, published guidance in 2019 acknowledging climate change as a factor requiring incorporation into marine hull pricing models. But the specific mechanism of cross-sea geography shift was not addressed. In that guidance, the connection between storm track shift and cross-sea frequency change is too recent a finding from wave climate research to have made it into actuarial practice. The shipping industry itself faces an adaptation challenge that has both physical and regulatory dimensions. The physical challenge is that ships designed and built today, with service lives of 20 to 30 years, will spend much of their working lives in a wave climate that is already different from the one that prevailed when the design standards that governed their construction were developed. The regulatory challenge is that the international framework for ship structural standards, maintained through the International Maritime Organization and the classification societies, responds to changes in the evidence base slowly, typically on timescales of 10 to 15 years between the emergence of new scientific findings and their incorporation into mandatory requirements. In a changing wave climate, this regulatory lag means that the fleet is perpetually adapted to the risk profile of the past, rather than the one it is actually operating in. The warming sea is not just raising the water level. It is reorganizing the weather that makes the water dangerous. The grid of cross seas will not disappear as the oceans warm. It will move to new latitudes, new longitudes, new encounters with ships that were not designed with those waters in mind. The mathematics of interference is indifferent to the atmosphere's composition. Two wave systems meeting at sufficient angles will produce the grid whether the ocean is a degree warmer or not. What changes is where those meetings occur, how frequently, and with what energy. And those changes, accumulating silently in the shifting patterns of storm tracks and swell climates across the 21st century, will arrive at ship hulls that, like the mariners and meteorologists of a previous era, were not entirely designed to see them coming. The knowledge the sea offers about itself is not given freely. It is extracted at cost, from wreck sites examined decades after the fact, from the memories of survivors with broken bones, from the meticulous re-examination of instrument records that no one examined carefully enough at the time. The history of maritime science is substantially a history of learning from failure, and the history of cross-sea science is no exception. The instruments that recorded the critical data were often not read correctly until after the ship was gone. The survivors who described what the sea had done in terms that did not match standard categories of wave behavior were not believed, or were believed too late. The knowledge that enables current understanding of cross seas was paid for in losses that, with that knowledge in hand, might have been prevented. The Ancon Project, analysis of North Atlantic cross-sea occurrences and near misses, was a research program funded by the European Commission between 2005 and 2009, specifically to address the gap between what wave science knew about cross seas and what the maritime safety community could operationally use. It brought together oceanographers, naval architects, maritime insurers, and ship operators in a consortium that attempted to move from the academic characterization of cross-sea physics to the practical specification of cross-sea hazard thresholds, numbers that could be put into operational guidance, routing algorithms, and structural inspection criteria. The program documented over 200 near-miss events from the preceding decade in which ships had reported sea conditions inconsistent with forecasted wave heights, and cross-sea analysis of the available spectral wave data for those events confirmed a bimodal spectral signature in the majority of cases. The near-miss documentation methodology developed by Ancon, systematic debriefing of ship masters and crews following anomalous sea events, combined with post-hoc spectral wave model analysis, proved capable of identifying cross-sea involvement in cases that had been previously filed under generic categories of severe weather or unexpected sea conditions. The methodology also revealed a consistent pattern in the descriptions offered by experienced mariners. Not the waves were too large, but the ship moved in ways it should not have moved. The vessel was struck from a direction that the swell did not come from. The roll was not synchronized with anything we could see. These descriptions, taken together, form a phenomenological signature of cross-sea encounter that is distinct from single-swell severe weather and consistent across multiple languages, vessel types, and ocean regions. The Ancon Near-Miss database provided the empirical foundation for a cross-sea severity index, a non-dimensional parameter combining the significant wave heights of both swell systems and the angle between them into a single number that correlates with the observed severity of ship modi. ONS and documented cross-sea encounters. This index, while not incorporated into mainstream operational wave forecasting, has been used by several European ship routing services as an internal filter for routing advice, a way to flag ocean areas where the wave model output, even at moderate significant wave heights, shows a spectral configuration associated with dangerous ship behavior. The survivors themselves carry knowledge that no instrument can replicate. Vera Santos, a Portuguese fishing captain who survived a cross-sea encounter off the Azores in 2007, described in a Portuguese Maritime Safety Commission interview the specific sequence of events that precede a serious cross-sea peak impact. First, a peculiar flattening of the sea surface lasting several seconds, an almost preternatural calm that she now recognizes as the destructive interference trough, immediately preceding a constructive interference peak. Then a rapid, widespread rise of water from multiple directions simultaneously. Then the impact, which she described not as the bow striking a wave, but as the entire vessel being struck from below by something that felt solid. She has not been able to convey this sequence to every crew member she has trained. The words available in the language of seafaring are not quite adequate for an event that does not fit the categories those words were developed to describe. The instrumental records left by cross-sea encounters on modern vessels are, if properly interpreted, substantially more informative than the historical record. Modern ships carry voyage data recorders, the maritime equivalent of an aircraft's flight data recorder, that log ship position, speed, heading, rudder angle, and critically, the three-axis accelerations of the vessel hull at high frequency. Analysis of VDR acceleration records from vessels that reported anomalous sea conditions shows a signature that is identifiable in retrospect. The simultaneous excitation of both pitch and roll resonances in patterns that cannot be produced by a single swell system, combined with transverse acceleration spikes at magnitudes inconsistent with the reported dominant swell direction. This signature is detectable by automated algorithms with sufficient reliability that it could, in principle, be used as a real-time on-board detection system, a cross-sea alarm triggered by the ship's own motion response rather than by external wave observation. The development of such an algorithm was proposed by researchers at the Korean Research Institute of Ships and Ocean Engineering in 2015 and demonstrated in sea trials using an instrumented research vessel in documented cross-sea conditions off the Korean coast in 2017. The algorithm was able to detect the onset of cross-sea conditions from the vessel's acceleration records, with a lead time of several minutes, sufficient to allow the navigator to initiate a speed and heading modification before the next serious peak event. The system has not, to the current author's knowledge, been commercially developed or standardized for fleet deployment. It requires only the already installed VDR sensors and a signal processing algorithm that could be implemented in the ship's existing bridge computer systems at negligible cost. The barrier is not technical. It is the absence of a regulatory mandate and the absence of a commercial driver in the absence of that mandate. The knowledge that comes after a cross-sea loss is, in principle, recoverable. The VDR data, if the recorder is located, and this is not guaranteed for deep-water losses, provides the acceleration signature of the final hours. The wave model hindcast provides the spectral environment. The structural inspection of recovered hull sections, when available, provides the fracture pattern signature. The crew debrief, if there are survivors, provides the phenomenological account. Assembling these data streams into a coherent reconstruction of a cross-sea loss event is technically feasible and has been done in several documented cases. What prevents it from being done systematically is the fragmentation of the investigative process. Marine accident investigation is conducted nationally by flag state authorities with varying degrees of oceanographic expertise, and there is no mandatory international requirement to conduct the spectral wave analysis that would identify cross-sea involvement even when the other data are available. Losses attributed to severe weather are not routinely re-examined against the wave spectral record. The knowledge sits in the data, unretrieved. There is a tendency in the communication of ocean science, and perhaps in the communication of all natural science, to treat the surprising, the dangerous, and the incompletely understood as aberrations, departures from a well-understood norm that will, eventually, be brought within the framework of established knowledge. The rogue wave was an aberration until it wasn't. The cross-sea was an aberration until the satellite record showed it occurring in 17% of ocean images worldwide. The tendency to classify the imperfectly understood as rare, when it may merely be invisible to the tools available to see it, is one of the most persistent epistemological problems in the study of the natural world. What the cross-sea teaches, if its lessons are received fully, is that the ocean's normal state is one of complexity, of multiple interacting systems, multiple sources of energy, multiple spatial and temporal scales coexisting in the same volume of water, and that the simplifications that make this complexity computationally and conceptually manageable are always, to some degree, misrepresentations. The single dominant swell is a useful fiction that serves forecasting and naval architecture well enough in most situations. In the situations where it fails, where the ocean's actual state is a superposition of two systems crossing at a dangerous angle, the fiction becomes a hazard. The cross-sea also teaches something specific about the relationship between visible drama and actual danger. The rogue wave that towers 30 meters above the surrounding sea state is terrifying, visually overwhelming, cinematically legible as a threat. The cross-sea grid, photographed from above, looks almost peaceful, regular, patterned, the product of a clean mathematical operation performed on water. The danger of the cross sea is in its structure rather than its magnitude, in the relationship between wave systems rather than the height of any individual wave. This is a kind of danger that human perception is poorly calibrated to assess, because human perception of environmental threat is calibrated primarily by scale and immediate sensory impact, rather than by structural complexity. The ship that founders in a 4-meter cross sea and the ship that survives a 6-meter single-swell sea have each been exposed to something qualitatively different from what their wave height measures suggested. The physical oceanography of cross seas has also illuminated aspects of ocean wave physics that were not previously accessible. The nonlinear four-wave interactions that Honorato and others demonstrated to be amplified in bimodal wave spectra had been theoretically predicted since the 1960s work of Klaus Hasselmann, but their practical significance in realistic ocean wave fields was unclear until cross-sea conditions provided a natural laboratory in which the interactions were large enough to measure. The cross-sea, in this sense, is not just a hazard, it is a probe, a naturally occurring experiment that reveals nonlinear wave physics that idealized single-spectrum laboratory experiments could not reproduce in the same way. The directional wave spectrum, the two-dimensional distribution of wave energy across all frequencies and directions, is now understood to be the fundamental observable of ocean wave science, the quantity that most completely characterizes the physical state of the sea surface and most completely predicts its behavior. This understanding, while it might seem obvious in retrospect, represents a substantial conceptual advance from the scalar characterization of sea state by significant wave height alone. The implication for the entire apparatus of maritime safety, forecasting, routing, structural design, accident investigation, is that the directional spectrum must become a standard operational quantity, not a research parameter. The tools to measure it, model it, and communicate it exist. The institutional infrastructure for making it universally available in usable form does not yet exist, or exists only partially. The ocean is not a surface. It is a medium, three-dimensional, layered, in constant motion at scales from millimeters to thousands of kilometers, carrying energy from sources distributed across hemispheres to destinations distributed across hemispheres, with the interactions between different energy components producing phenomena that emerge from the physics of superposition and nonlinearity in ways that cannot be predicted from any single component alone. The cross sea is one expression of this emergence, the specific, dangerous expression that occurs when two energy streams meet at the wrong angle in the wrong waters with the wrong ship in between. The old Polynesian navigators, lying in their canoes and feeling the swell with their bodies, were in some respects closer to the directional wave spectrum than a forecast chart showing a single significant wave height contour. They were reading the ocean as a multi-component system, extracting the signatures of different swells from different sources simultaneously. The sophistication was experiential and embodied rather than mathematical and computational, but the underlying physical reality they were attending to was the same one that modern oceanography has only recently been able to measure and model with comparable resolution. The ocean was always speaking in multiple voices. The difficulty has always been building instruments and minds sophisticated enough to hear all of them at once. The cross sea is the ocean speaking in two voices simultaneously, at an angle that amplifies rather than cancels, in waters that carry the memory of storms long finished, toward ships that were designed for a simpler conversation. The grid on the water is the ocean's grammar made visible, the structure beneath the surface, the mathematics beneath the waves, the convergence of distant causes in a present danger that, once you have learned to see it, you will never again mistake for calm.